Hey folks, Dr. White here. We're going to be doing some stoichiometry problems that involve gases. Number one, what volume does 16 grams of O2 occupy at STP? Key thing to remember here, STP means two things. Means that your temperature is 273 K and your pressure is 1 atmosphere. Now, at STP, remember that there's one relationship that always holds. At STP, 1 mole of gas, any gas, is 22.4, will take up 22.4 liters of space. So we've got 16 grams of O2. The question is, how much volume will that take up if I have 16 grams? Now, 16 grams, if we had moles, we could figure out how much space that would take up. So let's go ahead and turn 16 grams into moles. Well, if 1 mole of O2 is equal to 32 grams, how many moles are there in 16 grams? Okay, well, we just set up a ratio, right? Cross multiply, x is going to be equal to 0.5 moles. And that's what we're going to put up here. 0.5 moles. Guess what? We've got another ratio. Solve for x, and you're going to get 11.2 liters. So 16 grams of oxygen is going to take up 11.2 liters of space. Mixture of gases, 5 grams each. Calculate the volume of this mixture at STP. Now remember, STP, you're talking 22.4 liters of gas per 1 mole of gas. Okay, so let's figure out how many moles of gas we have, and we'll just turn it into liters using this conversion factor. This is called the conversion factor here. Okay, so 5 grams of O2. Let's see. 5 grams of O2. We're trying to figure out how many moles that is. But we know that there's 32 grams of oxygen gas in 1 mole. So this is our ratio. Okay, let's go ahead and solve for x. X is going to be equal to 0.15. Actually, check that. X is going to be equal to 0.16 moles of O2. Okay, let's do it for N2. Okay, we got 5 grams of N2. That corresponds to, we don't know how many moles. We're trying to figure that out. In N2, we do know that there's 28 grams of N2. If we check the periodic table, 28 grams of N2 is equal to 1 mole of N2. Okay, turn this into a proportion problem. Solve for x. We figure out that there is 0.18 moles of N2 in our sample. Okay, so this is O2, this is N2, let's do CO2. Okay, same exact thing. If we have 5 grams of CO2, that is how many moles? Well, if we know that there's 44 grams of CO2 in 1 mole, we've got a proportion problem. Cross multiply, x is equal to 0.11 moles of CO2, and then lastly we've got neon. 5 grams of neon is equal to x moles. Neon is 20.2 grams are in 1 mole. Make a proportion, cross multiply, solve for x. We've got 0.248 moles of Ne. Okay. Now, we want the total volume of this mixture, which means we need to take all the gases into account. So let's go up and add all of the moles up. So we're looking for moles total. That's going to be equal to 0.16. I'm going to do it this way. 0.16 plus 0.18 plus 0.11 plus 0.25. I'm going to just round that off. And let's just do some addition. We've got 0.70 moles of total gas. Okay. Now, we know that 22.4 liters of volume is taken up by 1 mole of gas. If I have 0.7 moles of gas, how much volume is that going to take up? Well, it's a ratio. Go ahead and do the ratio again. Solve for x, and we find that we're going to take up 15.7 liters of space with our 0.7 moles of gas. Next up, we've got a volume of gas at a temperature and a pressure. Looks like we collected it over water, and we have to take the water vapor pressure of water into account. Let's figure out how many moles of hydrogen gas are in the flask. This is your typical gas collection over water experiment. It's how chemists collect gas when they need to. Well, when I get a lot of numbers like this in a problem, I always like to kind of just know what I'm working with. 250 milliliters, well, that's a volume. 763 millimeters of mercury, that is a pressure. And looks like we have a temperature here. Okay. We also have a vapor pressure, right, of water. Sorry, that's pressure. That should be PV at a certain temperature, the same temperature. So let's go ahead and just write this out. So we've got V, that's 250 milliliters. That's also, by the way, a milliliter is the same as centimeter cubed. Did you know that? Pressure, 763 millimeters of mercury. Okay. Temperature, 35 degrees C. Let's go ahead and convert that to Kelvin, though. Let's go add 273 to it. It looks like we're at 307. If I'm not mistaken, 308 K. Okay. Well, we're looking for the pressure of hydrogen. Remember that the total pressure of the system is equal to pressure of both your gases. So the pressure of hydrogen plus the pressure of H2O. Let's go figure out what the pressure of hydrogen is. To figure out the pressure of hydrogen, we're going to need to rearrange the equation and then plug in. So we've got 763 total minus 42.2. We're looking at 721 is the pressure of hydrogen. Now we've got everything with respect to hydrogen, right? The volume, the pressure, and the temperature. Now we can go ahead and use our famous equation PV equals nRT. Okay? Question is, how many moles of hydrogen gas are in the flask? So I'm going to rearrange this. N equals, remember, because N is moles. N is equal to PV over RT, and then we simply just have to plug in. So our pressure is going to be 721 millimeters of mercury, but let's go ahead and I'm going to change this to atmospheres, and I'll tell you why in a sec here. Change to atmospheres. How do we do that? How many atmospheres is 721 millimeters of mercury? Well, we don't know, but we know that in 760 millimeters of mercury, we know that that's 1 atmosphere. So set up a ratio. Same thing we're doing. Solve for x. Point 948 atmospheres. I'm going to go ahead and put that in. So 0.948 atmospheres. Our volume, I am going to need that volume in decimeters cubed. So how many decimeters cubed is 250 centimeters cubed? Again, just set up a ratio. We don't know this, but we do know that there's 1,000 centimeters cubed in 1 decimeter cubed. X is going to be equal to 0.250 decimeters cubed. So 0.250 decimeters cubed, all right, over R. R, remember, is a constant. R is 0.0821 decimeters, atmospheres over mole Kelvin. And then finally we put it in our temperature, which is 308 K. Plug all that into the calculator. Turns out we've got 0.00938 moles of hydrogen. Moving on to stoichiometry problems. Here we've got a reaction. Looks like we're heating up calcium carbonate. The question is, if we have 4.74 grams of calcium carbonate, what is the volume of CO2 we're going to produce? Well, let's just go ahead and do our BCA table. Remember, BCA is before, change, and after. And this will kind of help us figure out where we're going here. Now, remember, if you're going to fill in the BCA table, we need to fill the BCA table in with moles. Okay. Now, the one number they give us is 4.74 grams. Let's change that into moles. Okay. So if we don't know how many moles of CaCO3 4.74 grams is, but we do know that if we have 100 grams of CaCO3, we know that that is 1 mole. We get that from the periodic table. Remember, if you're going to do this method, make sure that your units are the same on both sides. Then just make it a ratio. Cross multiply, solve for x. We're looking at 0.0474 moles of CaCO3. You could put that in the BCA table. Now, before the reaction, we start off with 0 moles of calcium oxide and 0 moles of CO2. What's the change? If we react 0.0474 moles of calcium carbonate, how many moles of calcium oxide are we going to produce, and how many moles of CO2 are we going to produce? Well, you have to look at the ratio. For every one of these, we make one of these and one of those. So I'm going to make 0.0474 moles of calcium oxide, and I'm also going to make 0.0474 moles of carbon dioxide. After the reaction, I'm not left with any calcium carbonate, but I have 0.0474 moles of calcium oxide and 0.0474 moles of carbon dioxide. Okay. Now, the question is, what's the volume of CO2? Okay. Well, I have the amount of CO2 in moles, but I'm not sure what the volume is. That's my x. Okay. But I do know that if I have 1 mole of any gas, that could be CO2, that's going to take up 22.4 decimeters cubed, or you could talk about it in terms of liters as well. 1 decimeter cubed is 1 liter. And then I can figure it out, right? I can just set up my ratio. X is going to be equal to 1.06 decimeters cubed of CO2 at STP. Okay, looks like we're doing another reaction. We're reacting zinc with chlorine gas, and it's looking like they're not going to be nice to us and give us an equation. We're going to have to write this equation out ourselves. Zinc metal reacts vigorously with chlorine gas. Remember that Cl2, it's a diatomic. 2 forms zinc chloride. Okay, now that's zinc chloride, but let's figure out what our charges are. Zinc is always plus 2. Chloride's minus 1. That means I'm going to need 2 chlorides here. Okay, that means we don't have to do much to balance our equation. The question is, what volume of chlorine gas at 25 C and 1 atmosphere is required to react completely with 1.13 grams of zinc? Okay. Well, let's fill in our BCA table, see where that takes us. Right? Now, remember, we need moles. Let's go ahead and figure out how many moles we're dealing with. Well, we start off with 1.13 grams of zinc. Let's figure out how many moles that is. So 1.13 grams of zinc. We're trying to figure out the moles of that. We know that in 1 mole, there's 65.4 grams of zinc. We get that from the periodic table. Set up the ratio. Solve for x. We get 0.0188 moles of zinc. Let's go ahead and put that in the BCA chart. Now, we're curious about, if we're going to react zinc completely, right, we're going to get rid of all of it, right, because it's going to react to form products. We're going to have nothing left. The question is, how much chlorine do we need to react with that? Well, the ratio is 1 to 1, so we're going to need 0.0188 moles of chlorine. Okay, so that's the key. All right, we need 0.0188 moles of chlorine. How do we get that? Well, we're dealing with a gas. All right, so if we know how many moles we have, I'm going to write it over here. We know how many moles that we want. Okay, we know what our temperature is. It's 25 C. Let's add that to 273 to get K. And we know what our pressure is. It's 1 atmosphere. Let's go ahead and solve the equation and figure out what our volume is going to be. Can you guess what equation we are going to use? That's right. PV equals nRT, where we're trying to find V. Rearrange the equation. Solve for V. So, n.0188 moles. R, remember R is a constant, 0.0821 decimeters cubed atmospheres per mole Kelvin. Remember T is 308 Kelvin all over 1 atmosphere. Okay, just for fun, you can go ahead and cancel out your units. Moles, moles, atmospheres, atmospheres, Kelvin, Kelvin. Put that into the calculador. It's looking like we're getting 0.476 decimeters cubed of gas. That would translate to 476 centimeters cubed of gas. Next up, we've got another reaction, stoichiometry. Looks like they're nice enough to give us an equation here, though. The question is, what mass of P4 will completely react with 2.5 liters of hydrogen gas? All right, well, let's go ahead and fill in our BCA table. Remember, we're dealing with a reaction. We need a BCA table. It's looking like we've got 2.5 liters of hydrogen gas at 0C, and 1.5 atmospheres of pressure. Now, one thing that I always look for, and I hope to see in a problem, is that we're dealing with gas at standard temperature and pressure. We can see here that those conditions aren't quite standard temperature and pressure. We've got 1.5 atmospheres of pressure. So that means we're going to have to do our ideal gas equation to figure out moles. Well, why do we need moles? We need moles because if we're going to fill out our BCA chart, remember the BCA chart only works when you're doing moles. So let's go ahead and do that real quick. Pressure 1.50 atmospheres. Volume 2.5 liters. Remember, that's 2.50 decimeters cubed, right? A liter is the same as decimeter cubed. R 0.0821, that's a constant. Decimeters cubed, atmospheres over mole Kelvin. Temperature, we're at 0C, that is 273 K. One thing that I always like to do when I'm doing these problems is I always like to make sure that units cancel out. If the units don't cancel, then chances are you got a problem. All right, atmospheres cancels. Decimeters cubed cancels. K cancels. We got moles, but it's in the denominator. It's in the denominator of the denominator. That makes it the numerator. That's what we want. We find out that we have 0.167 moles of hydrogen gas. That's what we can put in our BCA table. So 0.167 we start off with. The question is what the mass of P4 is. Well, let's go ahead and figure this out. If we react 0.167, how many moles of P4 are we going to need? Well, the ratio is 1 P4 to 6 hydrogens. So how many moles of P4 are we going to need? Well, just if you can't figure that out, let's go ahead and just set up a ratio. If we've got 1 P4 per 6 H2s, if we have 0.167 H2s, how many P4s is that going to be? Solve for X. We're going to need 0.0278 moles of P4 to completely react with 0.167 moles of H2. But the question doesn't ask about moles, it asks about mass. Well, we know how to get to mass, right? We don't know how many grams this is, but we do know that in 1 mole of P4, if we look at the periodic table, we get 124 grams. Set up the ratio, solve for X. We figure out that we need 3.45 grams of P4 to react with 2.5 liters of hydrogen. We are becoming effective chemists. Congratulations. Another stoichiometry problem. Here we go. Looks like they were nice enough to give us the equation here. It wants to know if we do 10.3 grams of magnesium nitride, we treat it with water, what is the volume of ammonia gas will be collected? Well, let's set up the BCA chart, kind of know where we're going here. 10.3 grams of magnesium nitride, that's this guy right here. We got to convert that to moles. Always, always, always. When in doubt, convert to moles. 10.3 grams of Mg3N2 is how many moles? Well, if we have 1 mole, we look to the periodic table, add up the atoms here. 3 Mgs, 2 N2s. Looks like we got 101 grams is 1 mole. Solve for X. We get 0.102 moles of magnesium nitride. Put that in the BCA chart under magnesium nitride. They're asking about the volume of ammonia gas. So let's go ahead and figure this out. Okay, I'm going to assume that water is excess. Okay, and let's assume that the magnesium nitride is fully reacted. What about ammonia right here, NH3? Before the reaction starts, I've got 0, but how much ammonia is going to be produced when I react 0.102 moles? You have to look at the ratio up in the balanced chemical equation. For every one of these, that's a 1, we get 2 ammonias. So if I react 0.102 moles of magnesium nitride, I'm going to make 0.204, just 2 times that, moles of ammonia. In the end, I'm going to be left with 0.204 moles of ammonia. So what's the volume if we're going to collect it at 20 C and 0.989 atmospheres? Well, we got to use our magic equation. PV equals nRT. Looking for volume equals nRT. Okay, so now that you've got your number of moles, you just plug it into the PV equals nRT equation. So N, we've got 1.02 moles. R, remember, is 0.0821. That is decimeters cubed atmospheres per mole Kelvin. And then lastly, we've got the temperature, which is 20 degrees C. That means we've got 293 K, right? Add 273 to that. All over the pressure, which is 0.989 atmospheres. Work that out, and it looks like we've got 2.48 decimeters cubed worth of gas. Okay, last one. Looks like we've got a reaction, nitrogen gas and hydrogen gas combined to produce ammonia. Let's write that out real quick. Nitrogen, N2, plus hydrogen is H2. React to form ammonia. Let's go ahead and balance this. So we've got 2 nitrogens. We're going to need a 2 here. We've got 6 hydrogens on the right. That means we're going to need a 3 here. Let's set up our BCA table. It's asking about what the volume of hydrogen gas is. So we're trying to figure out how much hydrogen gas we need. It's our X, okay? At those conditions to react with 10 grams of nitrogen, right? Now remember, grams don't really do too much for us. We need to turn this into moles. Let's go ahead and figure that out. 10 grams of N2 is X moles. We don't know what that is. But we do know that in 14 grams, we do know that in 28 grams of N2, that is 1 mole. So if we set up a ratio, we can solve that. And that is 0.357 moles of nitrogen. So that's the number that goes in here. Okay? If we're going to react that, we're not going to have any left. The question is, how much H2 are we going to need? Well, if we have 1 N2 per 3 H2s, let's work that out. If 1 N2, we need 3 H2s to react with that. If we have 0.357 N2, how much H2 are we going to need? Set up a ratio and solve for X. We're going to need 1.07 moles of H2. Now the question is, what's the volume going to be? Well, we need to use our good old PV equals nRT. Volume is going to be equal to nRT over P. And then we just plug in. We know we have 1.07 moles of H2. We know what R is, right? 0.0821. Over mole Kelvin. And we know the temperature, 25C, that is 298 K, all over our pressure. Now the pressure should be in atmospheres because that's what R is in. Let's convert that. If 1 atmosphere is 760 millimeters of mercury, if we have 735 millimeters of mercury, how many atmospheres is that going to be? Well, set up a ratio. Solve for X. We get 0.967. 0.967 atmospheres. If we solve this, we're going to get 27.1 decimeters cubed of H2. And that's the answer.